In this video, we are going to take a look at the Bohr's model. Please read the OER textbook chapter section 3.3 for more detail of this lecture. And after you finish watching this video, you should be able to start working on paper homework chapter 3, number 11 to 15. Please start working on it soon so that way you can finish it on time. All right, so this lecture chapter will pick up from the last video that we look at the atomic spectra, where you notice that different atom, when it's undergo electrical discharge, right, or when it's being energized, they all produce different color of light, right? We're looking at light in the as a photon or as a packet of energy that come, and we're looking at how the atom would absorb or release energy at a certain amount of energy as well in form of light, which is called photon, right? So that's from what we talked about last time. And in this lecture video, we are going to actually bring it back into the self-study in the chapter 2.1 when we talk about atomic structure. So before Bohr proposed the atomic theory, from the previous lecture section for the reading assignment, you learned that pretty much Rutherford is the one who discovered subatomic particle electron, right? And then Rutherford is also discover the nucleus within an atom, and he also discovered proton as well. And later on, Chadwick would discover the neutron. So those are the picture of the atom at that time. And no one actually addressed the location of the electron yet, but Bohr is the first person who actually addressed the location of the electron. So pretty much he is giving more detail of where the electron is located within an atom. So this theory is known as Bohr's atomic theory. So his theory is actually very helpful to understand why different elements would produce different color of light when it's, like after it's emitting the energy and things like that. Okay, so pretty much he described within his model, he described the structure of atoms and more specifically the location of electron as that electron would only orbit at specific energy levels. It's not going to go around like at any location as is desired, but it has to be at a specific energy level. And also when it's travel, it has to travel at a specific distance as well. Okay. And when the electron in the stable state, which is called ground state, it will not radiate, which means that it will not produce any light or any radiation. Okay. And electron will only change state from higher state to lower state, or from lower state to higher state when there is the energy is involved, and that energy that is being emitted or absorbed, we call those a photon. Okay, and it's going to radiate only when they are going from the higher energy level to lower energy level. Okay, so pretty much according to his proposed, we can describe that as in a picture that look like this, right? So if you have a nucleus, okay, the electron would, before Bohr atomic models, it describes electron, it doesn't have any like specific location, but Bohr specifically state that electron have to reside in a specific location or a specific energy level, and that is called n equal to 1. This n right here is referred as energy level. Okay, so this n right here is referred as energy level. So let me write that for a second. So this is the energy level. Okay, so that means n equal to 1 would refer to energy level equal to 1. So as you see, right, so we have nucleus, and according to chapter 2 that we learned earlier, in nucleus we have proton. Oops, we have proton. Oh, let me erase this. Okay, so we have proton and neutron in here. Okay, and then outside nucleus would be electron, right? According to Bohr's atomic model, electron would reside at specific energy level. So note that this diagram I'm using is for hydrogen atoms. Okay, so different atoms will be slightly different later on when we look at quantum number, but generally they are similar like this. Okay, so in this case, the reason why I specify as hydrogen atom, because hydrogen atom contain only one electron. So it's the simplest atom that we are going to look at because it's contain only one electron. So that's where it doesn't confuse you, right? Because other atoms are multi-electrons. They have more than one electron. So it's going to be a little bit difficult to address some of the what do you call, like, transition of the electron. Okay, so we're going to focus on only one electron right now. Okay, so that means this electron here can travel to, but it has to travel at a specific energy. And the next energy level that it can travel would be n equal to 2, n equal to 3, 4, and so on. And it can be n equal to infinity. So that would be the cutoff or the border of the size of an atom, right? So that would be, so if you measure from the distance from the nucleus to n, to what do you call, like, n infinity, that would equal to the radius of an atom, right? So that's what how people measure the radius of an atom. So pretty much electron can travel to all of those, but when electron travel to the n equal to infinity, that is actually mean that electron is being ejected. It's not hold together by the nucleus anymore, and that's what form an ions, right? Because a neutral atom, when it's lost electron, it would form ions. So that means once electron is being ejected, right, it's not part of the energy level anymore. It's go to the infinity, right? So it's go outside the radius of the nucleus. That's when the neutral atom will become an ion, right? So because ions is when when it's losing or accepting electron, right? So in this case, more specifically, it would be a cation, right? So that's what it means here. Okay, I'm going to take a look at the next thing. Okay, so for hydrogen, when electron is closest to the nucleus, or where it's in the n equal to 1, we call this ground state. Okay, so GS refer as ground state. Okay, so this is ground state. Ground state is the stable state because it's closest to the nucleus, which means the attraction force between the nucleus, between proton and electron, is strong, right? So it's most likely to stay around here because negative and positive are attract. So that's why this energy level would be the most stable for hydrogen atom, because electron want to reside closer to the nucleus. And the next state is not going to be the stable state now. It's going to be excited state. Okay, so, the next state would be excited state. And the first excited state would equal to n equal to 2, right? Because n equal to 1 is the ground state. The next one would be called first excited state. Okay, so this ES stands for excited state. Okay, and you probably can tell, right? If n equal to 3, it would be what, like second, right? And then 4 would be third, and so on. 5 would be like fourth excited state, and so on. Okay, so what I'm going to take a look at next is how electron can travel at different level of energy. So electron can travel to the different energy level by activation by the photon, by energy of a photon. Again, from what we learned from the previous lecture, photon is what, like light, right? So that means in this case, it can be activated through like the light energy, such as like UV light, for example, right? So once this electron is get activated, it's going to absorb that energy. Okay, so E stands for energy. So it's going to absorb this electron here, going to absorb the energy. And what happened is that electron would absorb and go to a higher energy level. It can be energy level 2, 3, 4, or whatever, but it's going to, this process called absorption, right? So it's going to go to a specific energy level. It will not stop in between. Okay, so it cannot stop between n equal to 2 and n equal to 3, or it will not stop between n equal to 1 or n equal to 2. It have to go all the way to a certain energy level. Okay, either n equal to 2 or n equal to 3 or n equal to 4. Okay, so it's have to absorb through and be at a specific energy level. And when it's fall, once it's absorbed energy, it's go to an excited state. The electron will be relaxed as well. Once it relaxes, it's going to give off the energy. Okay, so and it's going to fall down. Okay, so this process is called emission. Once electron is giving off energy, that energy is going to also come out in form of light as well, or as a photon, as a specific energy, right? So this photon light, as we learned from the previous video, that is equal to, you can calculate this value equal to h nu, right? Or the Planck constant times frequency. We also know that because the frequency is inversely proportional to lambda, you can also calculate this through the lambda as well, depend on what is given to you, right? So that means in this case, we can predict whether the light that is produced, what would be the color of it, right? Whether it's going to be red or green or yellow or whatever, by knowing either the frequency or wavelength of that, right? If you know the energy of a photon. Okay, so how do we know that? Okay, so that's what we are going to take a look at next. So we talk a lot about the energy level, that each of these are being energy level, but what are the value exactly, right? How can we quantify it, right? So that's what we're going to take a look at next, and we're also going to find out what type of light that is being emitted as well if electron undergo emission or absorption. So pretty much before we tie back into the energy level of each of those, the simple explanation of the atomic emission spectra from the previous video can be explained by Bohr model really well, especially for the hydrogen atoms. Okay, so pretty much when the hydrogen gas is get excited, right, it's undergo electrical discharge here, it's going to go up to, the electron of the hydrogen will go up to the higher energy level. Okay, so what happened after that is that once the electron in a higher energy level or in the excited state are relaxed, right? When they relax, they are going to fall off from the higher energy level to lower energy level, or sometimes to ground state, right? Or sometimes it's just to a lower energy level. Okay, so once that electron fall back to the lower energy level, a photon will be emitted, or which means that the energy that electron is emit, right, as it's falling down or as it's relaxed, is going to be emit in form of light. Okay, at different level of energy that is fall down, is going to produce different color of light. Okay, so that's why we see a different color here, right? If you have a diffraction grid right now to differentiate what are the color that compose in this, you are going to see this different color for the hydrogen atoms. Okay, so these different color associate with the transition of electron from higher energy level to lower energy level. For example, here, okay, this is for hydrogen atoms. So when an electron going from the energy level equal to 3 to energy level equal to 2, the photon, or the amount of energy of light that is produced, is going to fall into the red light range, which means it's going to give us like a red color as we see, right? When electron fall from n equal to 4 to n equal to 2, it's going to produce the energy that matching with the green light, okay, energy of the photon that matching with the green light. And when n equal to 5 fall to n equal to 2, is going to produce like blue, and so on, right? N equal to 6 to n equal to 2 would produce violet. So that's why we are seeing a different color because of that, because these are the transition of the electron from different level back to the lower energy state. Okay, so that's what it is telling us here. Okay. All right, so again, there are other photons that we are not able to observe by eyes as well. So that's why in this case, we are looking at only the visible light. There are other transition that is happen, and it might fall into the ultraviolet that our eyes cannot detect. Therefore, in this case, I did not include here, right? So for example, if you have the energy level that fall into n equal to 1, those are going to be the one that it would produce in the range of UV light and things like that. Okay, so, but in this case, we are going to take a look at only in the visible region here, because it's just a little bit clearer for us to see. Okay. All right, so this energy of the photon, so pretty much it's going to be related directly to the energy gap, or is the gap between the two levels, right? So for example, if we're looking at this energy of the photon here, okay, so this energy of the photon we call this E photon, okay, is going to equal to the energy gap. Okay, so it's going to equal to the energy gap. What do you mean by the energy gap? Okay, so the energy gap is the difference between the two states. So from n equal to 3 to n equal to 2, this gap of energy, right, because each of these are the energy level. So this gap right here, this is what we refer as the energy gap, okay, is going to equal to the photon. However, the size of the energy gap the difference in energy gap might not be the same as the size of photon, and we're going to talk about that later. Okay, so as you probably noticed that if I looking at the electromagnetic spectra, you will see that from what we know earlier, right? We know that the relationship between energy, frequency, and wavelength, right? For energy and frequency, they are directly proportional to each other. But energy and wavelength, they are inversely proportional to each other, which means that if you have a high energy, you are going to have high frequency, but you are going to have lower wavelength, right? So those are the relationship between these three. So if you're looking at this, right? So from red to violet, red would be the one that have the highest wavelength, okay? And violet would be the one that have the lowest wavelength. So that means if you think about the energy of the photon, it's just going to tell us that the energy of a photon of the red light would be lower than the energy of a photon of the violet, right? Because the two have different wavelengths in this case. So that means if you tie this back into the energy gap, it makes sense, right? Because the energy gap between n equal to 3 to n equal to 2, right? This is the energy gap right here. It's also different from the energy gap from here to here, right? So that's why in this case, this one have a smaller energy gap. That's why the energy of photon is also small. But this one have a large energy gap, right? That's why the energy of a photon is high. That's why the wavelengths come out to be in a low region of wavelength, and that's associated with the violet for this visible light right here. Okay, so the next thing that we are going to take a look at is we are going to take a look at the energy state of the hydrogen atom. So we're going to translate all of those and find out what would be like the value of it, right? So we can quantify the energy state of the hydrogen atom or of the electron in each energy level by using the modified Rydberg's equation, which is come out to be this one right here that you see. E subscript n is tell you about the energy of a specific energy level, right? Which n is a whole number, as you already see, right? N equal to 1 would be the ground state. It's going to be the one that is closest to the nucleus, right? So n equal to 2 would be further away, n equal to 3 would be a little bit further away, right? And so on. Okay, so this n have to be a whole number. And later on, when we learn about quantum number, this is what we refer as principal quantum number. We're going to take a look at this in the next video. Okay, so for now, just know that n is the energy level. Okay. How do we know what is the energy for that specific energy level? We can use this equation to calculate for that. Okay, so for example, okay, so let's take a look at example 1 here. For example, if you have n equal to 1, how can we know what is the energy of that level that electron resides? You can do this by plug in the number 1, right, for the n, or number 2 for the n, and you are going to obtain the energy, for example. So n equal to 1, you are going to do energy equal to negative 2.18 times 10 to negative 18 joule, right? And then 1 over 1 square, right? So you can do that. So when energy equal to 2, when n equal to 2, right, this is n equal to 1, this is n equal to 2, you can do the same thing, negative 2.8 or 18 times 10 to negative 18 joule. And then you are going to multiply by 1 over 2 square, right? Because that n would be 2 now in this case. If you plug this value into your calculator, what you are going to obtain would be, for n equal to 1, it would be negative 2.18 times 10 to negative 18. For n equal to 2 is equal to negative 0.545 times 10 to negative 18. Note that if you punch this in your calculator, you might get, let's see, I think I am actually moving a decimal point right here. So let me do 2.218 times 10 to negative 18, and then multiply by 1 over 2 square. Okay, so what I get from the calculator gives me negative 5.45 times 10 to negative 19. Again, these two numbers are equal. The reason for that is because if you just move decimal place, right, from here to here, you are going to decrease the negative exponent. So that's why if you move decimal place, what you are going to obtain would be this number right here. So that means they are identical. Okay, so this one and this one are the same. Okay, so these two values are the same. The reason why I have to move the decimal point in this case, because I want to keep the scientific notation, like the multiplier 10 to negative 18 to be the same. So that way when we compare the value, it's just easier for us to compare the value, right? Because right now these parts are the same, so the only thing we can compare would be just the number in front of them, right? So that's why I need to make sure that they have the same multiplier in this case. Okay, so now if you do the same thing when n equal to 3, 4, and 5, and 6, you are going to get this number. Again, the exponent here are 10 to negative 18 because I moved decimal place, because if you plug this in to your calculator, it will not give you 10 to negative 18. It's give you 10 to negative 19 or something, but you just have to move decimal place for this, move decimal point for this one. Okay, so what next then that we are going to take a look at? Okay, so this thing is going to refer as what we see earlier, right? So in this case, it would be if you have a nucleus, right? If you have a nucleus, the n equal to 1, right? So I'm going to actually write the nucleus on the opposite side, so that way it's closer to n equal to 1. So in this case, because n equal to 1 is right here, that means in this case, our nucleus would be right here, right? So it would be on top of this, so this would be nucleus, okay? Because our n equal to 1 is this level, right? N equal to 2 is this level, 3, 4, 5, 6, 7, and so on. And each of these level has this much energy. That's what it means. Okay. All right. So let's take a look at next. So okay. So now, if you consider the energy of each of those diagrams that we look at from example 1, what we are going to do next is we are going to use this to help us draw the energy diagram of hydrogen atoms. So this is the table that we just saw previously, right? So we just saw that in the previous slide. What I'm going to do is that I am going to find out the difference in energy between each of those energy level. Okay, how do I do that? Okay, so pretty much I'm going to find the energy gap, or the difference between energy level. If you subtract these two, right? So energy 2 and 1, if you find a difference between those two, this is the difference between those two. This is what we call energy gap, or it's the difference in energy between the two states. Okay. If you do the same thing for the rest of these, right? So I'm going to find out the difference between 2 and 3, 3 and 4, 4 and 5, 5 and 6, and 6 and 7. These are the number that you will get. Okay. So you probably notice something, that the energy difference between 1 and 2 is the greatest, right? And then it starts to get smaller and smaller and smaller and smaller as you increase the n value, right? So as the n value increase, you will see that the energy gap getting closer and closer and closer together, right? Because this one, the gap is the biggest. So that means between energy 1 and 2, if you have nucleus here between energy 1 and 2, it would be the biggest, right? Because it's the largest difference. Between 2 and 3, it would be a little bit smaller, right? Between 3 and 4 would be smaller. 4 and 5 would be even smaller, and so on, right? That's what this refer to, right? The energy gap is the difference between each of those energy level. If this is where the nucleus, right? If that dot is the nucleus. So now, what would the diagram of the hydrogen atom look like exactly then? Okay, so that's what we're gonna take a look at next. Okay, so we can draw this by, I'm going to go up on the opposite direction. Okay, so I'm gonna go from the bottom one would be lower energy and the higher one would be higher energy. Okay, so the energy is go up in this direction. Okay, so I'm going to put the nucleus down here because that's where the energy is at the lowest, because closest to the nucleus is the most stable because of the attraction between the proton in the nucleus and the electron. Okay, so that means the energy level equal to 1 would be closer to the nucleus, which makes sense that we already established, right? And the value of that, we already calculate 2 is equal to negative 2.18 times 10 to negative 18 joule. We already see that, right? You already calculate that by using Rydberg's equation, okay? Now, when n equal to 2, right, it's going to be in a different gap. You already calculate for this gap too, right? So we already calculate for this gap. What is this gap, right? So if you go back to the previous slide, you already see that these are the gap, right? So for this one is 1.6 times 10 to negative 18, right? So I'm gonna go back here. So this gap right here would be the energy gap that we just talked about, right? In between n equal to 2 and n equal to 1, okay? And we already see that when equal to 2 and when equal to 1, we already see that it's going to get the biggest gap. And when you increase number of n, right, the energy gap will get smaller and smaller and smaller. So therefore, in this case, you are going to observe the energy diagram to look like this, right? So as it's further away from the nucleus, the energy level of the electron will get closer and closer and closer to each other. Okay, so again, how do you calculate for each of these energy level? We already see that, right? You can use negative 2.18 times 10 to negative 18 multiplied by 1 over n squared, right? We already talked about that, okay? And the difference between energy gap is the difference between each of those energy that you calculate, right? So that's where it's coming from. Okay, so this would be a more accurate picture of the hydrogen atoms because the energy gap are not going to be the same. They are going to distance in a little bit slightly different size, right? So the one that is closer to the nucleus would have a bigger gap than the one that is further away. Okay. All right, so to conclude this in words, right? So I actually write this for you as well. So pretty much, as we already see, as you increase the number of n, right, the energy also increases. And if you increase the energy level, you will see that the spacing between the energy level becomes smaller. And hydrogen atom doesn't produce light at all wavelengths. It doesn't produce the continuous wavelength or produce all color of light because the energy level are discrete, which means that they are quantized, right? The electron travel at only specific distance or specific energy level. Therefore, it's going to produce only specific wavelengths of light. Okay, and 4 is that the transition between energy shells that are further apart in energy would produce the light that is going to have a higher energy and going to have a shorter wavelength and higher frequency, which is already addressed when we talk about the color, the different color of the hydrogen atoms that is produced between red light versus the purple or the violet light color, right? So pretty much this one is actually tell you that if the, so let me actually draw this so you can see it clearer. If you have nucleus and the energy level that is lower, right, and this is higher. If you have another one that is also higher, so when the electron travel from here to here, the energy gap would be smaller, right, compared to travel from here to here, right? The smaller energy gap would associate to the frequency of the photon that is going to produce in a lower region, but the wavelength would be a higher wavelength. That's what the number 4 is telling us. Vice versa, when you have a bigger energy gap, it's going to associate with the photon that is being produced as a higher frequency but lower wavelength. Okay, so that's what the number 4 is actually telling us here. Okay, all right, so now let's get into calculations. Okay, so that would be the conceptual part. Now with the calculation part, my expectation is you will need to be able to find out the energy gap and also associate that with the energy of a photon and calculate me the wavelength of light. Okay, so that's, or of the radiation. Okay, so that would be the expectation here. So example 2 asks us to calculate energy and wavelength of a photon that is emitted when electron in hydrogen atom transit from second excited state to the first excited state. Okay, so here is the energy level that we calculate earlier. Okay, so what we are going to look at is we are going to look at which one would be the second excited state, right? Because that's what we are going to take a look at, because we are considering the one that from second excited state to first excited state. So you need to know first n equal to 1. If you would draw the nucleus, right? If this is the nucleus, n equal to 1 is going to be the one that closer to the nucleus. And this is what we call ground state for hydrogen gas, right? N equal to 2 would be the first excited state. N equal to 3 would be the second excited state. So that means in this case, it's telling us that the electron going from second to the first, which means that this one is going to go from the second excited state to the first excited state. So that means it's going to imply that it's going to involve with n equal to 2 and n equal to 3, right? Because these are the excited state. Okay. So that means in this case, what you are going to do is you are going to find out the difference in energy between n equal to 2 and n equal to 3. Okay, so what we are going to have to know is that when we are calculating for the energy gap, the delta E gap like this, delta means difference. Delta, whenever you see delta, you are going to use the final value minus the initial value always. Okay, so in this case, our final value would be the first excited state, which is n equal to 2. Our initial value would be the energy of the third, n equal to 3, right? Or of the second excited state. Okay, so that's what we're gonna use here. Okay, so which means in this case, again, so subscript F would be final, subscript I would be initial. Okay, I'm going to just plug in the value that is given. So in this case, the final value would be from n equal to 2 or the first excited state. And then initial would be from n equal to 3 or the second excited state. If you subtract this, you are going to get delta E equal to negative 0.304 times 10 to negative 18 joule. Okay, so now this energy gap is not the energy of a photon. It's just the energy level in an atom. Okay, a photon is the thing that is going to be emitted, right? So as electron relax. Therefore, in this case, we are going to have to go to the next step. Okay, so this is the energy that is being emitted. From the previous step that we see, right? This is the amount of energy that is being emitted. You have to know that the energy that is being emitted is going to equal to the energy gap, which is going to equal to the energy of a photon. Okay, so that means when the electron jump from n equal to 2 to n equal to 1, is going to release energy. That's why this negative value is indicated, right? The negative value in front of the delta E, this negative value right here is indicate that the energy is being released. Okay. However, the energy of photon is the energy of what is being emitted, which means that is the energy of the light that is going to be given off for us to observe as different color, right? So this one have to always be positive. Okay. All right. So so in some other examples, you might get the delta E in a positive value. What does a positive delta E tell us? Positive delta E tell us that the energy is being absorbed. And how much is it going to absorb? Then it's going to absorb the same amount as the energy of a photon or of the light that is put into an atom. Okay, so pretty much you need to know that the energy gap, these are the energy of the transition of the electron, right? So if you have nucleus, oops, sorry. So let me draw this. So if you have nucleus, okay, when the electron travel, okay, so whether it's go up or go down, so if this is an electron, right, this is the energy gap, okay, which is the energy of an atom, the energy level of an atom. But what is being emitted? Okay, so if it's being emitted in terms of, let's say, like light, okay, so if this is fall and it's going to produce light, this is what that the thing that is being reduced or released, this is going to be a photon, and the energy of a photon will come out to be a positive value always. Okay, this energy gap right here is going to be negative when is emit that energy of the photon, right? If it's going from higher energy level to a lower energy level. However, if electron going from a lower energy level to a higher energy level, this is absorption. So the delta E would be the same value, except the sign would be positive, because indicate that electron is absorbed, right? Absorbed or added by that amount of energy. And where does this energy come from? Well, of course, it's going to come from some sort of the energy, right? So it can come from in terms of light, right? As a photon that is excited that, right? So this is the energy of a photon. For example, you can use some light to excite that electron to go up into a higher energy level. But whatever we do, note that the energy of a photon always have to be positive. Okay, whether it's absorption or emission, the energy of photon have to always be positive. But the energy gap, the sign would be different. Okay, you have to know the emission, the sign of energy gap would be negative, and the absorption, the sign of the E would be positive. Okay. All right, so in this case, all I need to do is that just changing the delta E, right, from negative value to positive value, because we are looking at the energy of a photon. Okay, so again, if you're looking at this, it's actually indicate that it's the wavelength. It wants you to find out the wavelength of a photon. Okay, so that means in this case, what we are going to do is that we are going to use this equation right here. Oops, which is this equation here is the equation of one photon that we talked about earlier. Okay, so this is of one photon. So we are going to use this equation in order to find out the wavelength, right? We already know the energy. Okay, so that would answer the first question here. We already know the energy of a photon. The next thing is we need to find out the wavelength. Okay, so we don't know what that is. Okay, so how can we do that? Okay, so we know that E equal to h nu. We also know as well that the nu, right? So let me, okay, so here we go. The nu also equal to C over lambda. So that means if you replace this term, okay, so if you combine these two, right? So if, oops, sorry, if I annotate here, let me annotate. So if I replace this into here, right, because they are equal, you are going to obtain the next, you are going to obtain this equation right here, right? So pretty much you are replacing the frequency by C over lambda, okay? And we are going to manipulate a little bit so that way the lambda would be on only one side, right? So you do cross multiplication. So lambda would equal to HC over E. Again, if you are not good at math here, you can just plug the value in and then try to find out the unknown variable. In this case, I just try to rearrange it so that way the unknown variable is on one side by itself. Okay, so by doing the cross multiplication here, right, between these two. Okay, so again, this one right here is in the denominator. I don't want that because it's our unknown variable. So you need to do cross multiplication so that way this one is on the other side and as numerator, not denominator. Okay, so plug this in. Okay, so I'm going to use this lambda equal to hc over E. So plug everything in. H is the Planck constant that we learned from the previous video, right? Multiplied by C is the speed of light, right? And E would be the energy of a photon that we just calculate, which is this one. This is the energy of one photon. if you do that, you are going to see that your your unit, right? So joule can cancel out, second can cancel out. You are going to have wavelength in unit of meter, which is the unit of length, right? So that makes sense. So in this case, if you calculate out, you are going to get 654 times 10 to negative 9 meter. It doesn't specify what unit, so you can just leave it like this. But on the exam, if it's asking you in nanometer, what you need to do is you need to do one more step, converting that into nanometer, and your answer would be in nanometer. So it's depend on exam, it depend on what unit this one would be given, right? So sometimes it would ask you in meter, sometimes it might ask you in nanometer. Okay. If you look up the electromagnetic spectrum, okay, so the scale that we have, you will see that these wavelengths right here would fall into red color. Okay, so it would fall into like about like red color. Okay, so if you want to know what is the what do you call it, what is the color that associated with that, right? It would associate with red color in this case. Okay. All right, so yeah, so this would give you a red light. So the next thing we are going to take a look at is we are going to, let me clear my drawing real quick. Okay, so the next thing we are going to take a look at is we are going to look at another modified Rydberg's equation, where the first one you already see, right? We already used this equation to find out the energy, the difference in energy between two states. You can find out the energy of the final state by plugging it into this equation, and also find out the energy of the initial state by plugging in this equation. And then you can subtract them to get the difference, right? Final minus initial, you're gonna get different. So this equation here, it just requires 2 steps. It just take longer on the exam, okay? So another equation I would like to introduce is going to save a lot of your time, is that what I'm gonna do is I'm going to replace this E final and E initial by this modified Rydberg equation here. So if I do that, delta E would be, this is of the final, right? So final would be N subscript F, okay? I'm going to subtract that from E of the initial, okay? So subtract that, and this would come from this term right here, okay? Except N would be the N value of the initial state, okay? You probably notice that these two values are the same, right? So this value and this value are the same. So you can take them out, you can combine the same constants, right? So if you take them out, what you are going to get would be this equation right here. So pretty much you can find out the difference in energy by using negative 2.18 times 10 to negative 18, and then 1 over the final state square minus the initial 1 over the initial state square. Okay, so that's, and this is what we are going to use often in order to find out this delta E. Okay, so you can use the previous method that you already see, or you can use this. Okay, so I'm going to show you another way to do this. Okay, so let's take a look at example 3 here. This example 3, we are going to calculate the energy and wavelength again. Okay, but in this case, it's involved with the transition of the electron in hydrogen atom from ground state to first excited state. Okay, so clearly ground state would be N equal to 1, right? And then first excited state would be N equal to 2, right? Because this is ground state, this is first excited state, okay? So that means in this case, if you're going from lower energy state to a higher energy state, this indicates that electrons have to absorb energy to go in a higher energy state. Therefore, this is going to be the absorption. This transition would be called absorption. The energy gap for absorption would be positive, which is going to equal to the energy of a photon as well. So that means if I want to cause the electron go from ground state to first excited state, we need to know what should be the light that we will need to apply to this, right? Or excited electron. So what is the energy of a photon that we require, right? So, and this energy of photon have to be the same as the energy gap, because electron cannot transit between the energy level, but it have to go to one level to another. So in this case, this energy gap have to equal to energy of the photon that we are going to input in order to excite electron. Okay, so I'm going to use another modified Rydberg equation where we know that the final energy state would be n equal to 2, right? So I'm going to replace that 2 with 2 square, and n equal to 1 would be the initial state. Okay, so pretty much again, we know that this is n equal to 1. All I did just replace that, right? This is the initial, this is the final. Calculate this, multiply by this term, you are going to get the energy gap equal to this much. Again, it's going to be positive value because this is absorption. Okay, so electron absorb energy. And this delta E is going to equal to the energy of a photon that is required. In order for electron to go from n equal to 1 to n equal to 2, it's going to require this much of energy because this is the energy gap, right, between those two. And where is this energy going to come from? It's going to come from the energy of a photon or of light that is required to activate that electron. Okay, so this energy of the photon, okay, is going to have a certain wavelength. And what is the wavelength for that? Okay, so wave one is that you can just plug in E equal to h nu and then use. So you are going to pretty much, you know this, right? You are going to find out frequency. After that, you use frequency, use speed of light to find out wavelength. So that's one method to do this. Okay. Another way to do this is you can just combine those together, right? E equal to hc over lambda, right? So you pretty much combine these two together, right? I prefer the way two because I don't have space on my slide, so I'm going to have to plug it all in one equation. So I'm going to I need to manipulate this equation the same way that I did earlier. I can do cross multiplication here to make sure that the lambda is by itself, because lambda is the wavelength, is the unknown variable. And all you need to do next is plug in the constant and also the energy that we have. Cancel all the unit, the lambda would come out to be 10 to negative 7 meter. If this problem asks you to find out in nanometer, what you need to do next is convert this into nanometer, right? So it's nano would be 10 to negative 9 and then report it in nanometer. If you look up on the electromagnetic spectrum scale, this nanometer is going to fall into the UV region, which tell us that for electron of the hydrogen atom going from ground state n equal to 1, okay, to n equal to 2 is going to require the energy from the outside. Okay, so it's the energy of a photon that is need to excite this electron, and that energy of a photon will come from the UV light. Okay, so pretty much what is indicated to us is that, oops, sorry. Let me erase this. Okay, so pretty much what is indicated to us is that if you want to activate this electron from the ground state to excited state, you will need to have it exposed to the UV light. That's what it means here. Okay. All right, so the next thing we're going to take a look at is we are going to take a look at the reverse process of it. Okay, so before you are given before you are given wait, let me erase this for a second. Okay, so before you are given the n value, right? So n final and also n initial as well, and you will need to find what the energy gap, right? And then you have to find the energy of a photon. Okay, and then you have to find either you can find out the frequency as well, or you can find out SC over lambda. You can find out wavelength as well. You can find out either frequency or wavelength. Okay, this problem here is the reverse process of that. So in this case, it's giving you one of these two. Okay, so either frequency or lambda, asking you to find out E of the photon. And then you are going to relate that to the energy gap between the two energy states that electron transit. and then it's going to ask you to find out the value of n. Okay, so that's what it's going to ask you. So this problem is the reverse process of that. Okay, so this problem is similar to homework 3 number, is that number 11C? I think I might get that wrong. So let me check that real quick. Actually 13. Okay, so I am, okay, so this is actually 13C. Okay, so what I would like you to do is, can you change this for me? This is actually similar to homework number 13C. Okay, it's not 11C. Okay, so yeah, so change that. Okay, so this is similar to that. Okay, so how can we do it? Let's take a look at what the information giving us first is giving us frequency. Okay, and it's tell us that the one n value asking for another n value. Okay, so pretty much we are going to draw the picture first, so that way it's help me see clearer. So we have nucleus, we have 2 energy level. It said ends up n, which means that your energy level would go from somewhere to n equal to 4, right? So it's n up to n equal to 4. And it also tell us that it's emit light, which going to indicate that electron would fall from the higher energy state to a lower, because emission is going from higher energy state to lower, absorption going from lower energy state to higher. Okay, so in this case, it's emit light, so it's implied that it's fall from higher energy state to lower. Therefore, your n value, when you calculate it, is have to come out to be greater than 4, right? Because it's higher energy level than 4. That's what it means. So in this case, why don't I include n equal to 1, 2, 3? Well, because the problem did not care about those energy level. That's why I don't have to include it. Okay, you can include it if you want to. It's just not necessary. Okay, so it's just not part of the calculation. If you do, it just take you a longer time. Okay, so I'm just gonna include only this section right here, because that's the only transition that we care. Okay, so it's tell us about frequency. Before, you have to find wavelength. Now it's giving us frequency, so which means that you can just use E equal to h nu, right? So plug it in. Okay, this is the energy that you are going to get. Wait, what is this energy again? Again, this is the energy of light that is being emitted. This is what we call photon, right? The light that is being emitted is called photon. Therefore, in this case, the energy that you have here is the energy of a photon. Okay, so make sure that this is emission. So E that you obtain is the energy of photon, but because emission, so the delta E have to be a negative value, because it's indicate releasing of energy of the electron. Okay, photon and electron are not the same. Okay, so that means in this case, what I'm going to do is that this is the electron. This is the photon, right? This is one photon. So what we need to do is that we will need to change that energy gap to a negative value. So you probably notice this is positive, right? But the energy gap have to be negative because it's emission. Okay, so it's emit light. Okay. All right, so what do we do next then? Okay, so in this case, you are going to go in the reverse process, right? Because now you know this delta E. The next thing we have to find out is we need to find out N. Okay, so that's what we're gonna find out. So I don't have space now, so I'm gonna have to go to the next slide. Okay, so I'm going to go to the next slide. So the next slide that we are going to carry on from the previous one. Okay, so this actually, again, 13, number C. Okay, from the previous step, we know the difference in energy between n equal to 4 and a certain energy level. Okay, we want to know, we know that n equal to 4 is the final, right? Because this is ending up to. So I'm going to circle this. This n equal to 4 would be our final. So that means what we are going to find out is we are going to find out the initial. This is what we don't know. This is what we know. And we also know this as well from this value. So all I have to do is I just need to combine them. So we know that delta E equal to negative 9.14 times 10 to negative 20 joule. Okay. Note that the negative sign is going to be very important, because whether your n come out to be correct or incorrect answer is depend on this side. If it's releasing energy or emit light or emit energy, these have to be a negative value for the energetic gap. But if it's absorbed, then this will have to be positive. Okay, so in this case, I'm going to set this equal to negative 2.18 times 10 to negative 18, and then 1 over final would be 4 square, okay, minus 1 over n initial square. Okay, so this is initial. What you are going to do is you are going to do one step at a time. If you are good at math, you can go ahead like do it, you know, like all at once, right? So, but this one, to just be safe, what you need to do is you need to do one step at a time. So start to divide both sides by negative 2.18 times 10 to negative 18. That's what I'm going to do. Okay. So these cancel out, right? Okay. If you do that, you are going to get 0.04193, which is going to equal to, okay, so what I'm going to do next is 4 square, right, is equal to 16. So in this case, it's going to equal to 1 over, oops, sorry. So let me use the black color here. It's going to equal to 1 over 16 minus 1 over n initial square. Okay. All right, so the next thing we can do is subtract both sides by 1 over 16. So I can subtract both sides by 1 over 16 in order to get rid of 1 over 16 from this side. Okay, what you're gonna get next is, okay, so let's see if I would have enough space here. These together, okay, so these together, you are going to obtain the next value equal to negative 0.0206 equal to 1 over n square. Okay, so it's n initial. Now you probably noticed that actually this is negative too, right? So I'm going to carry negative from the previous step. Right? So this is the negative right here that I carry over. So negative, right? So what you are going to do next is you are going to make sure that the unknown variable is on like the numerator side. So you can do cross multiplication here. Okay, so I don't have enough space now, so I'm just gonna go over this. So what you can do next is you can do multiply both sides by negative n square. Multiply both sides by negative n square. What you are going to get would be, okay, so this would cancel out, right? Negative will cancel out as well. Okay, so what you're gonna get on the other side would be negative n square multiplied by negative 0.0206. You are going to get 0.0206 n square equal to 1, right? Because you just move n square to the other side. Now, next one, right, keep doing further. 0.0206, divide that on both sides. Okay, you are going to get n square equal to 48.54. To get rid of square, you are going to do square root. Okay, so if you do square root of this, your n value will come out to be 7. Okay, so that means in this case, your n value would be 7. Which makes sense because if you go back to the previous slide that I draw the picture of the nucleus, n equal to 4 and n equal to 7 would make sense, right? Because 7 is higher than 4. So that means if the electron going from n equal to 7 to n equal to 4 is going from higher energy level to lower energy level, of course, going to emit light. Okay, so that would be the answer for this. Okay, so n equals 7 would be the final answer for this one. All right, again, so in order to practice more of this calculation, please work on homework chapter 3, paper homework number 13C for this part right here. Okay. All right, so the next thing that we are going to take a look at is the conceptual problem. So on the exam, you are going to see both calculation part and also conceptual part as well. Okay, so in this case, let's take a look at the conceptual part of the electron transition here. So we have different energy level and we have different transition that associate with different like n level, right? So what I'm gonna do is I'm going to go ahead, draw this first, and we're gonna do a summary later. Okay, so if I have nucleus here, think about this. If you have nucleus, right, we already know that n equal to 1 is going to be closer to the nucleus. N equal to 2 would be a little bit further away. And n equal to 3, the gap would get smaller, right? N equal to 4, the gap get even smaller. And n equal to 5, the gap get even smaller, right? So in this case, you will see that as you increase the number of n, the energy gap between each of those energy states would be different, right? It would get smaller according to what we calculated earlier. So now if you think about this, the energy level from N2 to N1, okay, so N2 to N1, okay, so this delta E here, compared to N3 to N1, which is choice B, okay, so from compared to N3 to N1, okay, so this is another energy gap. And another one is choice C, 4 to 2. Okay, so C is 4 to 2. 4 to 2, that's choice C. And then E is 5 to 4. It's between this one right here. 5 to 4 is really small. Okay, you will see that they have different energy gap, which means that the photon or the light that is going to associate with this transition would be different, right? Because we already know that the E photon is equal to the energy gap. So as we see earlier from the previous chapter and also what I mentioned earlier as well, the energy of a photon, right, is directly proportional to the frequency. Okay, so that means if energy increase, frequency increase, but it's inversely proportional to wavelength, which means the wavelength will decrease. Vice versa, if energy is decreased, frequency decrease, wavelength will increase. So that means in this case, without us doing calculation, you can pretty much tell by this relationship right here, right? So you can tell by this relationship. We are looking for the longest wavelength, which means that you are going to find the longest wavelength, which means that it's going to be inversely proportional to energy, right? Which is going to be inversely proportional to the energy gap as well, because a photon and the energy gap, the electron travel are the same, right? So pretty much are the same, but might be different size if it's emission. So that means in this case, if you want the longest wavelength, you are going to have to find out the energy gap that is the smallest. Note that the misconception of this part is that each of energy gap is the distance. It's not a distance. Okay, so that distance is not related to the wavelength of a photon. Okay, so these are the energy gap is referred as the energy level of electron. Okay, not of the photon. So therefore, the answer of this that have the smallest energy gap would be the transition between n equal to 5 or n equal to 4. Okay, so it would be D. Okay, so let me actually summarize this in a little bit better detail for this. Okay, so I'm going to pretty much you can just go ahead calculate this, right? We already did that calculation and then find out like wavelength at the end, right? That's take too long. That's why I have to use the analysis that we just did, right? So pretty much the longest wavelength is going to be the smallest frequency, which going to refer as the smallest energy gap, and the answer will still be D. Okay, so that's the explanation that I did earlier. Okay, so now let's pause a second here. What about this one then? Different transition, which one would emit light with the highest frequency then? Okay, so what do you think? Okay, so use that concept that I teach you previously to think about this one. Okay, so let's pause the video for a second and think about this and circle the one that you think that is correct. Resume the video again when you finish. All right, let's take a look at this. Okay, so again, if this conceptual problem, if it's multiple choice, you don't have too much time to do calculation. If you use this, it take way too long. Okay, so what you can do is think about the relationship between frequency and the energy gap, right? So in this case, if you want the highest frequency, you will need the shortest wavelength, okay? Which means that you are going to have to find out the largest energy gap, right? Because the energy gap is directly proportional to the frequency. So in this case, if you draw the diagram, the one that produce you the most or the highest or the largest energy gap would be from 3 to 1. Okay, so you can draw the picture out like I did earlier. Okay, so 3 to 1 would be the largest energy difference between the transition of the electron. Okay. All right, so for paper number 3, clarification before we finish up this is that I would like you to understand another unit that used to measure or used in measurement of the size of an atom. Okay, so in this case, when we talk about the radius of an atom, we can use angstrom. Okay, so which is this this symbol right here, A with the knot. This angstrom is pretty much mean 10 to negative 10. So for 0.76 angstrom, it just literally means it's times 10 to negative 10 meter. That's what it means. It's the measure of the distance, right? So I just want you to like think about that. Okay, so again, this distance right here is going to be similar to the energy level that we talked about earlier, but this distance will not be able to use to calculate the amount of energy. Okay, so it just tells you how far it is from the nucleus. That's all it tells you. Okay, so this number 12 is going to be similar to what we just did earlier when we talk about this conceptual problem right here, but it just gives you in a different form. Okay, so similar concept. Okay, so let's practice that. All right, so pretty much to review this, so far we used the Bohr atomic models to look at how electron resides in an atom. It have to reside in a specific energy level. When it travel, it have to be also travel in a specific level as well. And when it transit, the energy that is going to associate with that transition of electron, that's what we call delta E, or the different energy or the energy gap, okay, which is going to be directly proportional to the energy of a photon, right? So this delta E is referred as the energy that electron transit, right, between energy level, the transition of the electron. But the E photon is the energy of light that associated with each of those transitions. And this E photon, because it's light, is have wave property, therefore we can also figured out the frequency and also lambda as well. Okay, so that's what we learned about today. Okay, so pretty much you also learn how to calculate the energy difference between each transition of electron as well by looking at this equation here, right? Or you can find out specific energy level by using this equation. Okay, once you know the transition of the electron energy, then you will know that if it's come out positive, it would be absorption. If it's negative, it would be emission. But the energy of a photon have to always be positive. Okay, so again, the absorption and emission are involved with the transition of electron, but the energy that involved with the electron is absorbing energy or emitting energy. That energy that is being absorbed or emit is going to come out as the photon, which is have to always be positive. Okay. And this energy of photon can use to calculate either frequency or the wavelength. Vice versa, you can use either frequency or wavelength to calculate energy of photon and related that back into the transition of electron as well to find out the energy level that's what we saw in the last calculation problem. Okay, so again, so this video cover pretty much homework chapter 3, number 11 to 15. Please start working on your homework soon, so that way when you have any question you can ask me during the office hour.